Brian Van Straalen. I work at Lawrence Berkeley National Laboratory. I work on Chombo, which is a block-structured AMR library / framework. Down the hall from us is John Bell, Ann Almgren, Mark Day. They work on BoxLib, a very similar block-structured AMR package. There are other block-structured AMR packages in the Department of Energy. There's Samurai, there's Flash, there's parts of Carpet. But they all follow a very similar style in terms of data structures, parallelism, programming models. So, you learn one, you can learn the other pretty easily. Right, so let's explain what I'm talking about. We have examples, there's a cartoon in the corner of, here's a kind of X-ray view into a block-structured AMR region of a problem. In this case, on the planes, I'm showing the grid, and in the kind of black lines, I'm showing where boxes are. So block-structured AMR is, as it implies, you're doing adaptive mesh refinement, but you're doing it with little structured grids. So within a box or a block, you have a structured grid, but then you can tile space and refine and coarsen in order to achieve adaptive gridding. The goal here is to be as unstructured as necessary and not anymore. So this is an attempt to kind of balance between structured and unstructured. You want the ability to zoom in, but also you don't want to pay the price of being completely unstructured everywhere. It's the processors and the compilers alike uniform strided memory accesses, and you get lots of uniform stride 1 memory access in your algorithms this way, and then you pay a little bit of kind of fix-up price. So as long as the fix-up price is low enough, you do get a big win from AMR. So why and when? We now think of AMR as a compression before you've even discretized. So we had an observation many years ago from the visual and analytics teams, and they were whinging about the fact that when we transfer an S3D file, we get a big win from compression. We run compression, the file goes down like a factor of 100, and it's very easy to move it from our various labs. And they were complaining because our files didn't compress. I was like, they don't compress because we've already gotten rid of the entropy. There's a lot more information in the file because there's a lot more information in the simulation. So I said thank you, and had a new way of quantifying how good is the AMR. Good AMR means when you run compression on these files, they don't compress much. If you run gzip or fzip on this file and it compresses a lot, then you probably have you've got too much. There's too many things that are very near each other numerically, so you didn't actually get much compression in your algorithm. So you didn't get much compression up on the big machine. And on big machines, the big thing is less data. So here, there's lots of flops that not only did you not compute the flop, you didn't even load it into DRAM or move it up and down the memory hierarchy. So this is a very good way to simulate something without actually having a lot of data traffic. You pay for that by more complexity in your algorithm, but complexity comes up the instruction cache, not up through the data cache. So there's a lot more integer calculus that happens in an AMR code, but the integer unit tends to be sitting there idle. So I have a lot of power left in complexity, and that's how I get rid of most of my bytes. I get rid of a lot of DRAM traffic and a lot of DRAM on the DRAM side by doing compression. This is good when you have, so when this has happened, if you have lots of scales in your problem. So if you look at the previous one, you had intent shocks. Well, around intent shocks, Godunov's theorem tells you that you're always going to be dropped to first order. If you have a discontinuity in your simulation, you can't do better than first order accuracy. So you drive lots of refinement around that area, you make H very small, and then globally you can still get high order accuracy by isolating, it's the same if you have a fracture in your problem or any kind of, discontinuity in the coefficients or whatever gives you something that has jump conditions or jumps in your simulation. So these are like, order 1 delta function features you're trying to resolve. But you don't have to have delta functions in there. You can have anything that has a where more refinement would be good, but I only need it in certain spots in the problem. So I have people that are doing things like cosmic collapse. So you start with a uniform background of dark matter, in an early universe, and you say go. Well, in the very early running of that problem, things clump up a little bit, but if you look at the AMR grids that are generated, it looks like you're doing one of those eye tests. It looks like a fractal. And so there's lots of structure and all that. And I end up telling them, just leave it uniform grid for the first, mega year, because all that AMR is costing you more than you're winning. Like, you only cut out half the domain, but now you're paying all the AMR costs. So much later in the evolution, when you start getting a real clumping and strings and all the other kind of fine features, AMR is a huge win. And Astro is one of the first areas that strongly went to AMR. And you get deep hierarchies. You'll get 9, 10, 15 levels of AMR, because you literally have 8 orders of magnitude difference in densities in the late evolution. The flip side is complexity. So you've seen, you look at an interface for something like a linear solver, and it has put numbers into me, set some flags for me, go, right? You don't get that simple of an interface when you deal with block structured AMR. You need a much bigger interface with a much larger surface area, because there's many things you're going to have to control to do a good AMR simulation. So as a result, we tend to refer to AMR packages as frameworks, because we don't have just one or two or 5 entry point functions that we can document with huge header files. We have many functions we have to document, some of which you will use, and others you'll just leave in their default mode. But eventually, I have users that are into every single Doxygen header description I have in the code, because for their application, they needed to get in there. So that was one of our philosophies, is that there's no interface that we tell users you can't go past. So I have users that go all the way down into the base tools, because they need a different behavior from a very fundamental class to get their optimal code design. So, as a result, I had to provide support to people going up and down the entire call stack in our code. Usually don't start that way, but that's where many people end up. And you tend to develop an AMR code not from scratch. You tend to kind of flip through our examples, and you say, this one's close to what I want to do, and now I'm going to start changing, I needed, Hall MHD type simulations. So you go find our ideal MHD example, and you start adding your version of a Hall term. Or, yes, I want to use your, polytropic gas, but I have a different equation of state, and so I'm going to have to do a new cons to prim to cons, and I have to write my own Riemann solver. I'm going to replace that. But all the rest of the framework's fine. And that'll work until you change your physics again. And so over time, you'll be changing your physics and adding things, but you tend to start with a kind of base code, which is just a 1 epsilon off of the existing code base. So just to go over, I sent this in for the kickoff, and I don't think you guys got to see it. So this is just an example of some Chombo codes. So Charm is a dark matter simulation code that I work on with the ETH guys. MS Flux is a solar weather code, so the space weather from the sun up till about the Mars, up past and up to the heliosphere. Pluto is another astrophysics modeling code. It's doing mostly relativistic jets. Orion is a galactic formation code. This is Richard Klein at Berkeley mostly. Realm is a surface hydrology code. So this is a modeling the San Francisco Bay and Delta watershed and how the surface water works. The Plasma Wakefield Accelerator is doing a rarefied gas that's slacked with a laser. And this is for those desktop accelerators that they do, so modeling that kind of process. Chombo Crunch is a pore scale subsurface flow modeling code. So you take a chunk of what you want to model the flow transport for. You run it through something like an advanced light source, and you do a CAT scan of it. From that CAT scan, you get segmented image data. From that image data, we generate an embedded boundary, and then from the embedded boundary, we run a simulation on it. So straight from the experimental setup, and then they run a perfusion problem physically on that, and then we run a model from that, and we try to generate subgrid models from that type of calculation. We had a conjugate heat transfer problem for reactors. Cogent does, it's a fusion modeling code for doing edge plasmas. And Bicycle is a land ice code, so that's a active SIDAC project right now. And for everything up here, there's probably another factor of 5 codes that I'm not directly involved in. So these are just the ones that I'm occasionally in their code base helping them with something, and many of these I've co-authored papers on. I got the wrong slides going. So there's a similar list for the box lab codes. I'm giving them short shrift here. So they do Maestro and Castro, and LMC are their main packages. Maestro and Castro are supernova codes. And then Castro and LMC is a low Mach number combustion package. So that's doing, at low Mach number, you can use a projection method to turn the sound wave acoustic modes into a elliptic problem. And because you've now made the acoustic modes elliptic, you can solve that with the solver, and then you can take much bigger time steps, because now you can take time steps at the advective time scales and not at the acoustic time scale. So for a compressible gas, you often run at the acoustic time scale, and that means running at basically the speed of sound, which is very slow if you want to model a flame. So the flames, there's not much energy in the sound waves in a little flame, so you actually want to be at the advective time scales. Basic abstractions are data is distributed, so your data is distributed across an MPP machine. It's also distributed throughout the data hierarchy. When you want to actually do computing on a particular green patch, you fill in what your halo is going to look like, and it can come from your halo data can come from other processors, it can come from other threads, it can come from other boxes that are in your same address space but are possibly not within your same level of the memory hierarchy. And once it's been localized, then you compute on it. And this gives a simple interface for many of the functions you would override. So when you need to do a different kind of flux calculation, when you need to do a different kind of pointwise operation, you can, and we do all that choreography for you in the packages. So all the packages have ways of just saying, how many Go cells do you want? And go fill them now, please. And whether it fills it synchronously or asynchronously is usually a design decision that we have the options to go either way. And it just depends on how heavyweight is the function you're calling and how asynchronous do you think it can be. Let's see. Yeah, at this level there's no subcycling, and this kind of data abstraction is there for kind of the explicit advancing of the codes as well as for the implicit advancing. And I'll get into both of those modes in a little bit. But you're going to see, this is the box. So when you see the word box, that's a box. A box is a region of Z to the N, and it has a low corner and a high corner. So points in our world are infex, so a very cumbersome name as opposed to point. But point is a very overloaded math term, so we use infect. And 2 infects make a box, and a box layout is a vector of box. So very simple data structures. So here are the 2 packages I'm talking about. They're simple to download. My examples are going to be out of Chombo. We put out files that Visit can read, so does BoxLib. We do solves with Hyper and PETC, so does BoxLib. We have an interface with sundials that we use occasionally for experiments. And both of us under the hood do calls out delay pack in surprising ways. It's, we don't really do dense linear algebra anywhere in the code, but occasionally to build a stable stencil, we actually need to do things like SVDs. And, because in the code, you need to kind of compute your stability region. So you do that with, eigenanalysis. We're both packages that are based on MPI and OpenMP. We have side projects that do other kind of programming models, but the one you download as a release is going to be using those kind of programming models. And we're both mixed C++ plus Fortran. There is a all Fortran version of BoxLib. There isn't an all Fortran version of Chombo. Not everything's in that version, and there is both of us have done a binding to Python at various times. No one wanted it, so I've let it bit rot. If someone wants to try again, I still have my swig files around, so we can swig the code back up again, but the hooks are in place. And we use Doxygen to document all of our classes and all of our headers. In our code, we do a lot of software reuse by templating. So first there's kind of templated data holders. So a base fab is its only member is a T pointer and a box. So you can just tell us what your data type is and where you want it defined and how many components there are. So it has a int for how many components. It has a T pointer for your data type, and it has a box saying where this is defined. A particular example that shows up many places is the FArray box, which is a base fab of real, and real is type def to either double or float, depending on how you compiled the code. Now, the F in FArray box means the data is actually stored in Fortran order. So that one contiguous array, so we don't do C arrays, where you kind of go I, J, K as little square brackets. We just multiply all those numbers out and make one big allocation. Then when you hand that array into Fortran and then index using Fortran array notation, that's, if you go I, J, K, then the fastest, basically the thing to remember here is that the index that's changing the fastest here is I. So I is changing the fastest, J is the next fastest, K is the next fastest, and then component is the outer index. So it's a little kind of mental exercise you go through when you kind of look at that big flat array and think of, okay, I'm going to hand this into another package, right? I'm going to hand this into Fortran, I'm going to hand this into MPI, I'm going to hand this into a file I/O. So you have to remember that that's the way the data is laid out on the heap. We have others. So level data T is basically it's a vector of base fabs. So it is the data on a level. So when you see an AMR hierarchy, what you're really looking at is a vector of level datas. So this is our kind of global array object in Chombo. It's spread across the machine if you've given it if you've told it where the boxes go. And the basic parallel style here is boxes go to processors. And once you've dealt all the boxes to all the processors, now you're ready to do computations. There are other things like bin fab of particles. So we also have the next release will have our particle tools in it. So you can do things like pick algorithms with AMR. We have a paper in APS coming out of our description of how you actually do a convergent pick method. And once everyone's read it and we've got a new gospel, we'll be ready for some new users. So if you're planning a pick code, come talk to us.
In your slide, in the last slide, you said a data structure for embedded binary method. What do you mean by embedded binary method, and what is the created data structure for that?
That is a whole other talk. I don't have any examples of doing embedded boundaries. The Chombo release examples has examples of doing embedded boundaries, but the picture you have to have in mind is, so instead of an FArray box, you have an EB base fab, and you have an EB FArray box. And what that EB means is that it's aware of the fact that these cells are cut out by a geometry, and it's simple enough to do for simple cutouts. You still have the idea that the data, there's still one data value per cell in the FArray box. Some of them might be covered. So it's keeping track of that things are covered. Now, when you start actually doing coarsening and refining in AMR or in Multigrid, you have to keep track of the fact that you might have geometry that has a smaller resolution than even a cell. So some of the cells might be multi-valued. So the multi-valuedness of a particular cell is something else you have to capture in that data structure. So just like, and so instead of box is inside base fab, you have an EB box inside of an EB base fab. And the EB box knows about where the graph of the geometry is. So there's an unstructured data structure that you've localized through a second process. The EB geometry itself is distributed across the whole parallel machine. So it's a parallel database. And you say, for this box, what's my EB box? And so it queries the global geometry and it fills up your local graph. Once you've localized your graph, now you can just talk about you do a structured pass of your algorithm, then you do an embedded boundary fix-up. And that's the kind of structure of an embedded boundary algorithm, is you kind of ping pong between the general structured version of it and you sweep through your grid. And if there's no geometry in that box, you're done. You're going to run at basically the speed of, so you scale up basically with how much geometry you put in the problem. So for some problems, you have a lot of domain and just a little bit of geometry, but the geometry is critical for the dynamics. So you're gonna pay the computational cost just in those cells. My main application, which is Chombo Crunch, does exactly not that. I get basically fractal geometry, and the entire domain is filled with geometry. So I don't get the same scaling I would have liked, so I've had to figure out how to make geometry itself go fast. But I can actually show you examples after this. I have a whole other talk I can sit and go through maybe after the tutorials or during the tutorials. If anyone really wants to know about the embedded boundary methods and the embedded boundary code, I have a whole talk I gave at KAUST, and I'll just basically click you through that talk, and you can see if this is a technology you'd want to adopt. I didn't make a tutorial about it because it runs a little slow. So the example I'm going to give is basically, something in a box. But if your problem isn't something in a box, then you need something to represent the geometry. Again, this is f-array box. So you make a box. You can build two different f-array boxes. They have certain functions on them. BoxLib has the same object. So this slide works for both our packages. That's because BoxLib and Chombo diverged from each other just 18 years ago. So a lot of our classes have the exact same name. I think maybe even Samurai has some of the same named objects. Right. So you'll be doing blocked of grids dropped onto coarser grids, and you have certain properties with this, which is things line up. So your refinement ratios are powers of 2. So if you do refinements of 3, things start getting a little bit ickier. And I'll do another one. In our packages, there's no enforcement of some tree codes enforce unique parent-child relationships. But that's a little bit restrictive in terms of what kind of grids can I generate. You tend to get over-gridding in those types of packages. So Paramesh and Flash have that property. Batzaras has that property. For very deep hierarchies, it's not so important. But if you have somewhat shallow mesh hierarchies, the tree codes can be a little overkill. Uintah does kind of a blending of these two. So it does has this style, and then within this style, you can start doing trees. So we're looking at that as another idea. But the version of the release you get right now from BoxLib or from Chombo, boxes don't have to have unique parent-child relationships. Yes?
What defines the smallest patch that can be refined?
So you want to know things like, where are the cutoffs? So you tell it before it runs, what's the max level of refinement I'm going to allow? And there's a question of how small can boxes be, how big can boxes be. I have another slide about that, so I'll go get there. So bootstrapping, which is building up the initial hierarchy. So you start at the calculation, you say go, all you have is one big uniform box and an initial condition. So you're going to set the initial condition on the level 0, then you're going to do what's called tagging. So I've given a little snippet of the two main classes here. So AMR is kind of the orchestrator of the calculation, and it's going to call your various AMR levels at various times in the algorithm. So the first thing it does is ask level 0, can you tag some cells here based on whatever criteria that you've put in. It's a virtual function, it's physics dependent, you have to decide what is important about your calculations. So oftentimes an undivided difference is a good approximation for an error estimator, but you can do a full-on a posteriori error estimator of your current solution if you want to. This doesn't tend to be expensive. You give the tags back to us, we have a way of generating the patches from those tags, so we'll generate where those patches are, and then we'll call your code again, saying at that level, can you tag the cells that are not right on this level now? And then we'll generate more tags. Well, it's going up, there's an up and down process here. And at the end of it, so you go up, you go down, up, down, up. Because you have to have proper nesting at the end of all this. And then we're going to tag those based on the efficiency, and then you get various, the efficiency factor says how much of that box has to have tags in it before I'll drop the box in. So at higher efficiency, boxes will conform closer to your tag sets, but you will get funny in smaller shaped boxes. So low efficiency gives me big uniform boxes to compute on. High efficiency, I get lots of AMR efficiency, but I might pay the price because there's too much interbox communication or interbox calculation happening. So each box will satisfy these kind of 2 criteria. So I tell it that there's a max box size that you shouldn't be violating. So n is any dimension in the box. And there's a blocking factor. So blocking factor is how chunky should these boxes be. So we tend to put a blocking factor of 8 or 16 in. And that says that in any given dimension, the amount of grid is a multiple of 8, multiple of 16, multiple of 4. And that tends to give you this kind of nice chunking of boxes. You don't get little 1 boxes, and it's not a 1 by 8 box. It'll be a 4 by 8 or a 4 by 4. And that's important for when you actually compile the kernels in your algorithm, because that's what the compiler is going to look for when it wants to build things like vectors. So this vectorizes and uses the cache lines very well. You don't tend to want a blocking factor smaller than a cache line, for instance. So if you know something about your machine, a cache line tends to be 4 words or 8 words. So if you're doing a scalar calculation, you might want a blocking factor of at least 8, because that way each pencil in these boxes, each line in the stride 1 direction of I is a cache line. So you will get good cache use if you have a blocking factor that's near what your cache line is going to be. Or you're going to realize that something like I have a 256 wide vector unit in my machine. Well, you probably want something that hits that vector size very consistently. So when you're doing point-wise updates, you'll hit it very consistently. So, older machines didn't care so much. Newer machines are caring more. We also do things like now, even when you have your box, we actually do the calculation tiled. So there's another level of kind of granularity in the code, which is subtiling. But we haven't made that part of the release yet. We'll be part of the next release. So I won't get into the tutorial, but you can ask me about it during the tutorial or Q&A session. We are also adaptive in time. So when you're adaptive in time, you do have, you don't just move the whole AMR hierarchy at a time step. What you tend to do is what's called subcycling. So in step 1 of the algorithm, you advance the course grid to the new time at the course grid time step. Then you advance the next finer level and then you recursively ask, do you have a finer grid? And then you ask, on those finer grids, what advancing do you have to do? So you can kind of see how the algorithm plays out. So those are the steps of the algorithm. And each time, once you've synchronized with the level below you in time, your idea of what the flux through the faces were is different from the course grid's idea of what the flux through that face was. And you're going to have to do what's called refluxing, which is you're going to have to correct the course grid flux based on your actual fine grid flux. So if you don't do that, you end up getting the global accuracy of the course grid. So that's bad, all that AMR for nothing. So you actually need to use the fine grid flux on coarse fine faces. And so we have machinery called Flux Registers that help you do that. So as you're advancing the algorithm along, you're shoving things into the Flux Register. And at some point, you've reached synchronizing, and you tell it, okay, go now reflux. And it finds all the places in the course grid where you need to do the refluxing. And you can see that knowing where that refluxing is supposed to happen can be quite complicated, because these faces here are going to need the reflux. And they're not on a course grid face. They can be in the middle of a box. That weird interface on the lower level is a complicated data structure. It might not even be on your processor. So you're going to sometimes this involves sending messages. Sometimes part of it will be a message, and another part of it will be a local copy to a local data structure. So these are all broken up into little pieces. And the Flux register under the hood is a very complicated object. This is part of the reason why at some point people stop writing their own AMR package, because to make that performant is very hard. So you have box layouts. So I have a collection of boxes, and you can iterate over these in two different ways. One is the layout iterator, which will visit every single box in the layout. One is the data iterator, which only visits the boxes that you own on your own process. So when you're doing kind of a SPIMD programming model, you will mostly be using the data iterator, which says, for my rank or for my thread, only iterate on the ones that I own. There are places in the code where you'll use layout iterator. I don't recommend it for most users because you automatically are creating an order n algorithm every time you talk to that layout iterator. So when I do things like under the hood for computing what the motion plan is going to be for when you do an exchange or you fill go cells or you're going to do a level fluxing. I've had to play many tricks knowing things about the kind of Morton ordering of these boxes underneath you so that I can do these things in n log n time. So the n log n versions of the algorithms are hard to get right. If you spot in your profile something that's growing like n as you add boxes, you probably have one of these order n operations somewhere, and you should probably come talk to us because we have some tricks that we can share with you about that.
I have a question.
Yep.
When you do reflux, does the user have the freedom to control that, or just specify the way you reconstruct the flux, or
there's an interface that says, give me fine fluxes. There's an interface that says, give me coarse fluxes. And there's another interface, there's a function you can override, which is how are the two resolved. So you need a unique value for that, right? It's a finite volume scheme, so you have to all agree on what that face value is going to be. In terms of moving data from sources to destinations, you probably don't want control over that. As far as I know, there's only been a couple people that have wanted to change how the Flux register works, and it has to do with so if you want to do constrained transport or some of these things, some of these algorithms are face-based or node-based, and they're exact, and you want to preserve that property. So rewriting those in AMR requires a different kind of Flux register. So we have a couple different ones. So kind of go through the menagerie that we have. If it doesn't do what you want, there might be one there that's pretty close to what you want. And again, you can always, derive from level Flux register, override the functions that you think should be doing something different, and try that out. Right? There's none of these interfaces are private, so you can always derive from it. Make it public, try something out. In general, you have objects that help you with things like there's interpolators, fine interpolators. So getting data from coarse grids back to fine grids, those are interpolators. We have several varieties of interpolators depending on what your algorithm needs are. I've seen some rather sophisticated ones in my time. Some of them, it depends on what your conserved properties are as to what your interpolator ought to do. But here's using an interpolator, interp to fine. We have a similar class which goes the other direction, which is coarsening. This is averaging, so this is for a second order scheme that's doing where your cell centers are your values at the cell centers, then averaging is fine. If you're doing a fourth order volume average scheme, averaging doesn't work like this. Averaging is actually, averaging is exact in that case, so there's no truncation error in that operation. So depending on what kind of discretization you've set up, Sometimes averaging is exact, sometimes it has a truncation error. You have to kind of know your math to know which one's going to do what. That's also one where you have to kind of read the manual to know what you're trying to do. So there's a large section in the Chombo manual that describes these objects, because these objects all are important for getting your algorithm right. And then there's, this is filling in ghost boundaries with interpolation. So sometimes your ghost cells come from your other boxes. Sometimes your ghost cells come from, and sometimes they're going to come from the level below you. So here you have a case where some of your ghost cells could get filled at your own level, and that's what you prefer to use. If you hung off the edge and now you're taking data from the coarse grid, it's actually quite important not to grab the cells that are covered by your own box. So there's a lot of gymnastics that go on to, in that little re-entrant corner, grabbing cells in kind of a directional fashion. If you grab the cells that are under you, there's actually a feedback loop, and you actually drop order. And that's, for most second-order schemes, it's a very common mistake for people implementing AMR. It's at fourth-order schemes where I can go back to grabbing data from underneath me because I have exact coarsening. But in the presence of inexact coarsening, you've committed a h² error in that averaging, and now you're going to grab it to form a stencil to fill a ghost cell in the cell next to you. Well, now you've dropped down to h. And if you have a second-order scheme, now you're committing an order h error on all of your boundaries. So these are things you got to be somewhat careful about. Our classes do that for you for second order, and they do that for you in fourth order. So in fourth order, it's okay to grab the cell underneath you and use it. In second order, it's not okay. And then there's Philpatch. Philpatch fills the ghost cells of the guys above me as well as the cells inside of me. It's a more elaborate version of the interpolator, but inside it's using the interpolator. The other extra piece of this is that if you have a fine patch, and you can remember in subcycling, I went from a coarse patch, and the first thing I did was I advanced it forward in time. My intermediate patches need their ghost cells filled with data from those coarse and fine patches interpolated in time. So this handles the idea that the coarse grid is a coarse space-time grid, and it's going to interpolate onto your face at the correct time. You're going to end up correcting that all during the synchronization phase, but you will actually evolve the fine grids wrong if you don't do this space-time interpolation to fill those ghost cells. So this handles space-time interpolation to fill ghost cells from a coarse grid that has a coarse and a fine time state. Yes?
I'm just trying to get clear on what the relationship between the coarse and the fine grid is in the solve. So is there constrained approximation happening between the fine and the coarse grid? It sounded like you were sort of doing a separate solve on the coarse grid.
Well, there's two types of algorithms that we have in there. There's the Poisson solvers, and then there's the explicit time advancers, the Godunov schemes, the Riemann schemes. So in the explicit advance phases, you are going to be needing this kind of boundary condition to get filled. And the fine grid, the only way that the fine grids hear anything from the coarse grid is this guy. So they get initialized before they start with the interpolator. Then they're going to advance forward in their little subcycle times, getting their boundary conditions filled by this time-space interpolator. And when they've reached the same time space, then the coarse grid gets corrected based on what the fine guy's fluxes are. When you're doing an elliptic solve, there's no time anymore, right? So what you're going to end up doing is but there's still multigrid. It's an AMR multigrid. So the AMR levels and the multigrid levels are kind of ping-ponging around. So if you did a refinement factor of 4, then there's a factor of 2 multigrid levels sitting in between 2 AMR levels. But let's say you did factors of 2 refinement. So there's an AMR level, AMR level, AMR level. You do the multigrid algorithm, but every time you come back, you have to correct the flux on the level below you. So you still need to do this kind of correcting. You have to reflux during a solver, but you don't do space-time interpolating. So that's the main difference. So the refluxer is reused in the multigrid, and is an important part of it. You won't converge correctly without it. And that one's not hard to see in the code. Actually, AMR Poisson is an easy enough class to read that you can see where the refluxer shows up. Often what we'll do is we'll rewrite the problem in a residual correction form. So we'll compute the residual everywhere, and then and then that's the right-hand side for the Poisson solve. And so built into that residual was all the mistakes at coarse-find boundaries. So the residual actually holds the information. So when I do a solve, you'll see I have a homogeneous coarse-find interp, because I can keep saying, I know that the error equation has a homogeneous boundary condition at every coarse-find boundary. So I actually don't talk between the levels with during the inner part of the solve, just on the outer residual calculation. For nonlinear solves, that doesn't work, but for linear problems, it works great. Level flux register. I've gone into this, but I'll just describe it again. You're going to have to, so the U update at the coarse grid is the U at the coarse grid, the delta T at the coarse, find it at the coarse, and then subtracting what all these kind of sub fluxes that came out of the flux register. So the basic idea is the flux that was on the coarse grid is not accurate enough to maintain global accuracy. So you do this kind of like, you update it with the coarse flux, and then later on you subtract the coarse flux and add the fine fluxes. So the reflux function and the level flux register are keeping track of the bookkeeping for you. Sometimes people will use the default parameters will do this operation. You can use the flux register to do other types of calculations, and then you change what the scaling factors are. I wouldn't recommend that for kind of casual users, but if it's an algorithm where you really are concerned about changing how things happen at coarse-find boundaries, this is the object that at least knows where they all are and knows where it's going to stick it in data objects. So you don't have to figure that part out. Right, Chombo Fortran is as I said, we do mixed C++ and Fortran. This is code from the day when the Fortran compiler was really the fastest compiler code generator for structured grid computations. It is much less true today, so I've written some of these things now in C, and they run as fast. But really, Fortran as a domain-specific language for array computing makes a lot of sense. I get nice syntax for this here is nice syntax for talking to a multidimensional array. C and C++ do not have a native object for multidimensional array, which is ridiculous. And people like it. People like using I, J, K to talk to arrays, and they like, people understand loops. People know what this does, right? Unfortunately, if I write code like this, then I'm going to have a version of my function for 2D. I'm going to have a version of this for 1D. I'm going to have a version of this for 3D. I'm going to have a version of this for 4D. So we ended up having directories full of blah.1.f, blah.2.f, blah.3.f. And you'd fix a bug in the 2D one and forget to do it in the 3D one, and now you're way down the road. So Chombo Fortran is a set of macros that let you write this loop once, and if you write it correctly, then you get kind of dimension-independent Fortran. So we process this through Perl. It'll generate Fortran code based on what dimension you ask for. And it also has a bunch of handy things like from your Chombo Fortran code, we'll generate header files that you can then include in your C++ code so that you can call the Fortran code. And you won't get, Fortran doesn't care if you get the order of the arguments wrong. It compiles and runs, and it's just a horrible bug to find. So to stop that process, we'll build the prototype, and then when you compile the C++ code, you will get a compile error. If you've got the order of the arguments wrong, if you didn't call something const when you were supposed to, if you put an int where a float was supposed to go, it won't compile. It's also where we automatically stick in timers. So you don't have to actually instrument your code anywhere. All your Fortran code has timers wrapped around it. But yeah, this really gets rid of a lot of kind of bugs you can make in your code. We also have a kind of built-in geometric multigrid inside of our Chombo code. all of our codes, all of our examples are basically semi-implicit algorithms. Chombo and BoxLab were built for transient problems, so you're really not going to find us doing any steady-state problems. For steady-state calculations, Chombo and BoxLab and Samurai, they're all overkill, right? I could get to a steady-state answer very fast using some other numerical method. So we're very focused on doing time-accurate, transient problems. I think that's going to be where most people do their scientific computing in the future. But you really don't want to be doing purely explicit codes, right? So some packages worked for a long time. Like Flash didn't have a solver in it for probably the first 8 years of its existence because their problem space was just the explicit algorithms. But eventually gravity is important and you have to kind of get with that, or viscosity is important, or Euler's equations only solve so much. If you want to do a conservation constraint, or you want to use a projection method like Chorin's projection methods, eventually you want to take larger time steps. So larger time steps means you do asymptotic analysis. Asymptotic analysis will tell you which time scales are not energy bearing. Non-energy bearing scales, I can step over them. But every time I step over a non-energy bearing time scale, I generate a new elliptic term in my PDE. These elliptic terms have to be solved implicitly. Most of them look like Poisson's equation or variations of Poisson's equation. So we've built in our own geometric multigrid into Chombo that you can call. And this is actually a Helmholtz operator. That's Helmholtz, that's variable coefficient Helmholtz, and that's a viscous tensor operator. They all derive from AMR level op. And those AMR multigrid knows what to do with these types of operators, and it'll execute our geometric multigrid algorithm for you. You'll see, typically we like our codes to execute one time step in about 1 wall clock second when you watch it executing on the machine. That's usually where the balance point is for I'm using enough processors, I have enough parallelism, I'm running big enough, and I'm using the resources efficiently. If you're taking much more than 1 wall clock second to get one time step in your model, then maybe you needed more compute power. But in order to kind of make that, but that's the kind of times we need to simulate, that's the kind of speed we need to simulate problems of interest. And if we kind of dropped too far behind that, then, like climate, for instance, you really do need to get, so many years of modeling out per minute. Otherwise, you're not actually, if you get down to a minute in a minute, well, now you're not actually predicting the weather, you can just watch the weather. So you have to go faster than the thing that you want to model looks like. So some problems have hard constraints, like you can't be predictive if you can't go faster than a certain speed. Most of our applications are in that I should get about 1 time step per a real wall clock second. And if you have a couple elliptic solves in there and it's a big problem, that means I need to be able to do an elliptic solve on the order of a half second, a quarter second. So that's really hard for a package like PETC or Hyper to do. I mean, that's, getting a solve in a minute is actually a good for most of these kind of, explicit matrix packages. So because we know a lot about our operator, and we know exactly how to solve that problem, and we know exactly what relaxation to use, I've run, full Titan simulations with, 400 billion degrees of freedom on Titan with like 1.5 second solves. So at the time I didn't realize it, that was the fastest solve in the world, and then now in the meantime someone's done bigger and faster, so I didn't get my Nobel Prize or my Gordon Bell Prize, but I forgot to tell anybody. So, but that's the kind of speed that we expect from our multigrid when it's a well-behaved Poisson operator. When you're not a well-behaved Poisson operator and you still have to solve it, so you have either strongly varying coefficients, so you're doing flow through a porous media and the connectivity changes sharply, or you're doing a combustion problem where near the flame front the densities are changing rapidly, or the energy transfer is going up and down by large amounts, regular geometric multigrid will start failing on you. So in the poor scale flow problems, our multigrid starts crapping out. It can't actually solve that problem. It stops converging. So you have to switch to another solver. So we've done, we call Boomer AMG, and we do it through the PETC interface. So PETC interface, this is a lot of material. It's basically, you will go from our matrix-free representation to the explicit matrix representation, and that basically looks like these two classes. So there's PETC comp grid, which takes our problem domain, our boxes, and our ref ratios, and so it basically gets the structure of our AMR hierarchy. And from that, it's able to turn our vector of level data of FRA box, so that's the data living on our hierarchy, and turn it into a PETC vector. And it can go the other way around. It can take a PETC vector and fill up our level data right-hand sides. And then when you derive from this object a operator, so this is the Poisson operator, it knows how to create stencils, and then it can hand you back the matrix. So this is a linear operator. So if it's a linear operator, I can turn it into a matrix. And now I have a matrix and I have vectors. I can call any of the other functions I like in the KSP interface of PETC. So what we really do in the code is our full AMR hierarchy problem has too many degrees of freedom to build the matrix. So we do one round of our geometric multigrid, reduce the problem size by a factor of 64 usually, and then we build the whole matrix and then call out to a package. So that still gives us, it's a little slower than what we like, because we're adaptively gridding, we have to keep throwing this object away. And we have to keep throwing these matrices away, because these matrices keep changing every time the grid changes. So setup costs are a big thing for us. But at least you can do this. And when you're really debugging a problem or trying to get some kind of handle on things, I can take this matrix and I can ask things like, I can do an SVD on it. I can see if I have strong negative components. I can see if I have, bad eigenstructure. Am I actually building an unstable operator? So this actually allows us to do much better analysis of our problems, because I can actually get the linear operators. Then here's an example of, this is what create stencil for Poisson looks like. It's doing basically, shifts and directions and weights. So a stencil operator, stencil tensor is a weights and shifts in a stencil space. And at every point, at every infect, it can build up what's the stencil at this point. And then it uses that vector of, it uses this internal structure which maps positions in our grids to points in PETC's int space. And you can go back and forth with that. So this lets us kind of map things into a flat, it lets us do the flattening you need for linear algebra. So this is nice. We didn't have this in Chombo 3, and this is something that's released in 3.2, which is what you all have access to. And we've beefed it up in 3.3. So in the fall, there'll be a more beefed up version with more operators and more abilities to compose things with matrices. Oh, yeah, I actually have an example of calling Krylov method things. So your example that you'll be running is a polytropic gas problem. It's doing Euler's equations. So this is doing just explicit hyperbolics. It's a second order Godunov scheme. It's using PPM as the discretization method, if you're familiar with these techniques. It's using an inexact Riemann solver for the Godunov method. The source code is over, so you have two direct, so you have Chombo, example, and then you have AMR Godunov, and in there you'll find exec ideal, which is for an ideal gas. You'll find straight Euler. You'll find exec polytropic. So I can look at anyone's plot of this problem, and if they run out to a particular time, they blow it up for me, and I can tell you what's wrong with your code. So this is one that we kind of mentally can do. Oh, you didn't get Van Leer limiting right, or you didn't do flattening right, or you didn't actually compute your Riemann problem right. And they all have a signature that you can recognize in this plot. So the actual plot looks like the mock here. I've kind of turned it on its side. Is what you'll be doing. The shock has come in at 30 degrees, and for various grid resolutions, you can see how much resolution you're getting. This is a very fine resolution. You can see along this Mach line, you're getting a Kevin Helmholtz instability. you're getting a roll up off of the surface. This is a no-slip plane here. This is the unshocked region where you haven't actually, the shock hasn't reached here yet. And you're getting this, we call it a mock snail. So it's a very lovely structure. You need to find all these regions. There's a rarefaction shock, there's a compression shock, there's a mock line, there's a moving rarefaction in here. And if you've done anything wrong in your Riemann solve, that this area starts looking too much like this area. If this starts rolling up the wrong way, then I know that you're not doing limiting right. So it's a very interesting problem. I've set up the tutorial ramp problem to do this as a 2D. Factor of 4 refinements. There'll be 3 levels, levels 0, 1, and 2. It'll run out to 100 time steps, which is just before this amount of time has elapsed. If your max wave speed calculation is incorrect, then you might run past 100 time steps. So in here, you're actually computing the max wave speed, so you can actually compute your next fastest legal time step. So I have a fill ratio is the efficiency. There's a blocking factor, as I mentioned before. There's a max grid size, I've set to 32. These are things you can play with. So you can play with what the refinement ratios are. You have enough time to play with the blocking factor or play with the max block size. There's also a min box size. I haven't set it. So if you actually want to force a minimum box size, if you want fixed box sizes, then you just set blocking factor equal to max box size equal to min box size, and every box will be the same size. So some people like to run that kind of model because it maps back to other algorithms. So if you want to have codes and grids that look like what Flash gets, you just set these values to be all the same, and you'll get basically the grids that you would have gotten from a tree code. So that's handy for people doing kind of cross-code comparisons. And if you change the ref ratios, you'll see kind of changes and variations. You can't really see the grid lines here because the grids are so fine that the lines have just are overlapping. But in Visit, you can zoom in. But these are plots made in Visit, and you'll be able to use Visit on your output files if Visit's working. So I'm hoping that'll be the case, and that should be it. So questions?
How do you feel about high-order DG methods? So instead of having one solution value in a cell, I could have 125 to 4,000 solution values in a cell.
Discontinuous Galerkin, I did that in my thesis work. I haven't found the win to be worth the effort, so I think there's an efficiency issue. We have 4th order and 6th order versions of doing AMR, in which case you get more. The hardest thing to do with any of these for higher level explicits is it is hard to do limiting correctly. So positivity preserving and limiting both get hard, and DG doesn't actually fix any of those problems. So it doesn't fix the hard problems, but it makes higher order and higher accuracy more amenable. So I liked them at the time, but now that I see how many things go wrong in these kind of simulations, I need my old toolkit. My old toolkit of FCT, Van Leer limiting, flattening. All these techniques are just I've never figured out how to do them in spectral correctly, and DG has a bit of a spectral feel about it, right? And I think that's what's hiding in behind there. Is I think if you actually scope through the code, you're going to find what the We Know guys find. Is that there's little over and undershoots oblique to your main shock. So in 3D, you'll see there'll be a front moving this way, but if you actually take cuts to the problem in a diagonal plane, you'll find Gibbs phenomena, and it's out of the plane of the discontinuity, and it's really hard to get those to damp out right. It's the cross derivative terms.